Right. So in this session, we are going to talk a bit about handling project constraints and dealing with project uncertainties. So we do make a plan for a project, but things not always go according to plan. There may be um, some unforeseen risks that could materialize because of weather. We could encounter difficulties. So how do we face those sort of uncertainties in order to bring the program back on track? So we will start with the review of the first problem set, which was discussed in the previous session, and the key learning outcomes from that was to use critical path method for decision making, a review of probabilistic and deterministic scheduling. So deterministic scheduling is where we definitely know the duration of different activities. For instance, foundation is definitely going to take 3 weeks of time, whereas probabilistic is where subcontractors do not give you a deterministic time frame, rather they give you a probability. So for instance, groundworks could take anywhere between 2 to 5 weeks duration based on the weather conditions. So a probability is given. So in that case, we do probabilistic scheduling. Then I talk about project acceleration. So sometimes when projects face uncertainties, we may have to accelerate subsequent activities to bring the project back on track. And how do we deal with project changes? So we are looking for some of these learning outcomes. Now, if you remember when we concluded the previous session, one of this problem was given to you to reflect. So the this problem basically it was aimed to develop certain uh, outcomes. Firstly, how to convert a method statement to a network diagram. So here the process and a method statement is given, and it was expected that students would go through this method statement and convert it into a network diagram. Secondly, the learning outcome was basically to draw a project network diagram. Thirdly, to undertake CPM computations, and fourthly, resource balancing. So these were the learning outcomes which were expected from this project. So we would start by just quick read through the problem as it was given. So it stated that the project will start by a drilling of well. So we know that the first activity we could put here is uh, drill well. Okay, the once the well has been dug, you should start pump house construction. So we can see it's a very simple finish to start relationship, and we would follow it with pump house construction. So it was expected that students will read through this method statement, and very often you would have a meeting with your subcontractors. You will ask them, maybe using an on-screen board, to identify what are their constraints, which work they require finishing. So based on this, you would create a method statement which will be eventually converted into a network diagram. Likewise, you could see also the duration is given. So for instance, the first activity has a duration of 4. The second activity, once you could start pump house construction, has an activity of 3. So we can use this information to start the CPM computations. So just a reminder, while manually scheduling a project, we assume the project starts at day 0, and then we keep adding the duration. So as a 4 weeks, so this will be completed by the 4th day, if that is the unit we are considering. And if a pump house is a 3 days activity, it will be starting after the 4th day and will be completed on the 7th day. So just by simply reading the method statement, um, um, the idea was that students will convert it into a network diagram. So we will look at one of the sample solution to this problem, just to get you start thinking. So here we see in the description, the project will start by drilling of well. So here we have included a milestone activity at the beginning. So very often if you are using a software, it uses a diamond symbol to indicate a milestone activity. And here you could see the symbols, and the duration of a milestone activity is 0. So this is just a milestone activity. It doesn't signify anything. Then if we read the description, after starting of the project, we will have it will start by drilling of well. So this is the first activity. Once the well has been dug, you should start pump house construction. So we can see the pump house is following drilling of well, and installation of pump, which is over here, should only be done once pump house has been constructed, and plus 8 days lag. So there is a little bit of a variation in this solution which is being presented here, and the problem, so that you are thinking while you are doing. So it's not exactly precisely the same solution to the same problem, but it is very close to the one which was discussed last week, and an 8 days lag. So the next one is once pump house has been constructed and should only be done. So here you could see and power line laid. So this is the power line laid task, which has a duration of 3 days, and installation of pipe will begin once excavation work has been completed. So for excavation work there was no predecessor, so this is the first activity beginning, and this is followed by installation of pipe. So basically, just by reading through the method statement and understanding the predecessor relationship, we will draw a network diagram. So there may be slight variation, which is acceptable. So we could as you see how the CPM computations are done. Just a reminder, we have discussed it. So while manually scheduling a project, we always assume the project starts from day zero. So you could see all of the initial activities are starting from day zero. Now, if you are using a software, the software will prompt you to specify a specific date. So you could say, for instance, my project is starting from 2nd of March, or it could be any day in the future. The next thing is duration. So we basically add the duration to give us the, so this is the start time, and we add the duration to give us the early finish. So 0 at 4, 0 at 3, give us the early finish for activity power line as 3, and for excavation early finish would be 5, and with a duration of 2 for delivery of material. The early finish for activity delivery of material will be 2, and then this early finish becomes the early start of the subsequent activity. So we will take this thing over here, and we will add 4 at 3, which is 7, and likewise this 5 would go here, and here in this particular case, in this example, it's a start to start relationship. So we do not have to finish for the foundation to for the excavation to finish. So the arrow is not coming from this direction, rather arrow is originating from the beginning of this activity. So this is more like a concurrent activity with some sort of a float built into it. So we wait 3 days after excavation and has begun, and we could start pouring the foundation. So we do not have to wait for the entire excavation activity to finish. I think this, I'm not sure if this 10 is correct. It should be 7 here, and then okay. So based on this, you will uh, draw the network diagram, and so your solution could look slightly different from this one, and we'll calculate the forward and a backward pass. So this is a further illustration of other activities, and based on this, so we have gone through this process of doing the forward pass and the backward pass previously. I'm not going to repeat here in this case, uh, but essentially what we do is we just complete the forward pass, which helps us calculate the early start and the early finish times for all activities, and then the early finish of the last activity becomes the late finish of the last activity, and then we do a backward pass where we are subtracting the duration, and which helps us calculate essentially the late start and the late finish timings. Okay, so far so good. Now, once we have done this network diagram, then we can basically see what is our playing field. So this is an initial version of the bar chart or the Gantt chart, and it is basically telling us, first of all, what is the possible duration. So if you look at the first activity, drilling of well, the early start was 0, and the early late finish is 11. So essentially, we have got in theory the time between 0 to uh, the 10th day or 10th week of our project to schedule it, whereas the actual duration of this is 4 weeks. So it is our discretion whether we schedule work on the early start dates, and then we would have a float at the later. But if we don't want that, we could possibly enjoy the float bit early on, and possibly uh, schedule our work on the late start date or somewhere at the middle. So this is our playing field basically. Likewise, for delivery of materials, it's a 2 days activity, and then we have got, if you look at this, this is early start and this is the late finish. So we have time before the end of week 5 to schedule this activity. Sorry, if we are using a unit of day, so it will be day 5. For excavation, here you could see the float is 0. So just a reminder, we calculate the float by subtracting the box at the top from the box at the bottom. So the formula for uh, float is early finish minus uh, early start, or late finish minus late start. So either you subtract this box from the top, from the box at the bottom, or you do it for the finish times. So we can see that excavation, for instance, has 0 float, which means that excavation is a critical activity, which is, that's why it's shown in the solid color. There's no room to play here. There's no flexibility. This work has to be scheduled if you want our project to be completed by 15 days. So this is particularly an activity where there's no flexibility. Likewise, for power line, if we look at and the power line, the early start was 0 and the early finish was 14. So we have got time from 0 to day 13 to schedule this work, whereas the actual duration is 3. So we have got a possibility. We could enjoy, for instance, we can have a float, and then we can schedule the work during the middle, and then we could have maybe a float carrying on towards the end. So this is our playing field. And foundation, you can see, is a critical activity. So this is an initial version of the bar chart. You could print it out if you want to explore different configuration. Right, so there are two possibilities. Either we schedule work on the early start timings. So here by star, we are indicating the days on which work will be undertaken. So here the project manager has taken a decision to schedule all the work on the early start dates. That's why it's called early start Gantt chart. And it's a good practice as well, because you will have a lot of a float. So your project will be less risky if things take slightly more time. If your delivery of materials take not 4 but 6, again, you will have enough float and you will still be able to deliver the project within the 15 days duration. So the decision was taken to schedule the work in early start dates, and we have work scheduled all on the early start timing. So the star indicates these are the work days, and all the float is towards the later end of the activity. Right, so that is one possibility. The other possibility is we could schedule our work based on late start timings. So here you can see the project manager is using all the float upfront, whereas the work is being scheduled towards the end of each activity. Now, obviously, if you take this option, your project is more risky. So what about if the drilling of well doesn't take 4 days, and rather it ends up taking you 5 days? If that is the case, if you have a 1 day delay, that would mean that as there was no float, your project will not be able to be finished in 15. So you will jump over at 16. So it is not a recommended method of scheduling your activities, because you are making your work and your project much more sensitive. Anyhow, it tells you the other extreme ability. So one extreme is to schedule all the work based on early start timings, and the other extreme is to schedule it based on the late start timings. Now, there was a bit of a resource element into this problem as well. Each activity in the problem description has certain resources attached to it, and in this case we assume the resources are workers. So drilling of well, it was given in the problem description, has got 4 workers working through the entire duration of this activity. The delivery of material required 4 workers for working for the 2-day duration. The excavation material required 5 workers. Right. So we use this information to produce what is called a resource loaded graph chart, so bar chart. So within on the bar chart we have our resources loaded, and then we can produce a monthly breakdown of resources. So sorry, a daily, so if that is the unit of time. So on day 1 we would require 19 workers on our side. Day 2 we would require 19. Day 3 it is 18, and all of a sudden on day 4 we have to fire 6 workers because we will not be requiring this, and then we on day 5 we will just require 2 lesser workers. Right. So usually this sort of arrangement where there's too many peaks and troughs is not seen as a good resource profile. Ideal world, we would like to work with the same amount of workers. Maybe for instance we take a balance of 13 workers, and we use the same resource throughout the project, but that may not be most efficient manner, or that may not be possible. But nevertheless we will try to achieve a resource profile which is closer to the balanced one. So here for instance, if we look into this sort of a resource profile, we could see what about to reduce the resource demand from 19. What about if we delay some of the activities? So for instance, a power line. Okay, so because we have got a very healthy float here, so what about we move power lines slightly later when there is a slightly lesser resource demand? So if we take 6 from here, that would reduce the resource demand to 13, and let's take it here because we could schedule work slightly later, so that would going up by 18. Again, this is a very sharp spike, but we can take it slightly later, so we can play around with it to see how we could get a bit more a leveled resource profile. So in this arrangement, which is shown here, certain decisions are taken by the project manager, which is resulting in not an ideal world situation, so not a consistent 14, but you could see slightly smoother resource profile, not as much fluctuating as was the previous example. And the way it is done is by using the float within the power line activity. So the work was postponed. Here also the decision was taken to use the float on the assembly of tanks, and also some usage of float on the installation of pipes to get a slightly better resource profile. Okay. So in this example, we learn how to draw, first of all, the network diagram, then how to do CPM computations. Okay, so the question is, would you diminish the resources and extend the duration of one or more activities? Right, so the whole idea is this is just a tool to help you have a deep think to explore what are different optimization opportunities. So what you are suggesting is a possibility. Again, you will have to possibly discuss it with the subcontractors who are responsible for this. Possibly you could see, so your project would have certain constraints. For instance, your client may have specified that they definitely want the work done in 15 days period. Now, if that is the case, that is your constraint, and you would not like to reduce the duration, because if you reduce the duration, that will double the amount of time. And if it is, for instance, excavation activity where you have got no float available to you, reducing, so rather than bringing 5, if you decide to bring 2 people, that would possibly double the amount of work required on excavation. So on the non-critical activities, yes, if it is possible, again, that would depend on specific project conditions. Sometimes you have got specialist workers working. So for instance, the worker was brought in by a foundation subcontractor cannot be good enough to be doing the work of delivery of material. There may be different teams. So all what I'm saying is yes, you have to explore different optimization opportunities. And what it is that this allows you to have this opportunity to explore it with your team. Okay. Here in this problem, we didn't give you that flexibility of diminishing the resources and extending the duration. So it has been specified within this problem that the resources are fixed, and you just use them a float wherever available to optimize the allocation. Right. So moving on, if you click, so this has been distributed as a week 3 session note. So if you check on the module website, and if you click on the this icon, you should be able to access the Microsoft project solution, which is done by one of the previous students, right? So uh, maybe sometime we could do it manually, and then perhaps compare our manually done schedule with the one performed by the computer and see the difference. So with the computers it is much easier. You do not have to worry about all those things, like computing the early start early finish, or late start late finish timings, or the bar charts, or for instance the resource graph. Everything is done for you by the software. Having said that, some students jump to the usage of software without having a understanding, so we always recommend that students manually solve a problem. This way they get the confidence, they know what they are doing, and once you know, perhaps then you can use the software to maybe compare your solution with the one which software has provided. All right, so we have discussed the CPM. The other concept which we will touch upon is the program evaluation and review technique. So the difference between the PERT and CPM is related to the definition of task duration and consequently the project duration. CPM adopts deterministic values, whereas PERT is considered probabilistic or stochastic method. So in the previous example which you saw, it was given that foundation work is going to take you, for instance, 3 days, right? So, but if you speak to a lot of real world contractors, subcontractors, they're not going to give you a deterministic value. That may put them in an odd situation if they say that, well, the work will take 3 weeks and then they fail to deliver it in 3 weeks period. So very often they would come up with a probabilistic value. So they will give you an idea that my work will take between 1 to 5 weeks based on these are constraints, and also based on the contractor having done the job properly, and maybe on the weather condition or so. So for that, once we are given the probabilistic value, we will be using PERT technique. So PERT is used when there is a high degree of uncertainty with individual activity duration estimates. PERT applies the critical path method to a weighted average duration estimate. Values are considered. So within a PERT calculations, there are 3 times which we considered. One is called the optimal time, the other a pessimist time, and third the probable time. They are distributed according to a beta curve, which is not a normal probabilistic curve. So just to revise the differences between deterministic and probabilistic scheduling, we will go through 2 problems to review what these are and their differences. So the first problem relates to deterministic scheduling. So here we have been given a deterministic time by the subcontractors. So this problem description reads: a new apartment building is required to meet requirements of a growing student population at a university. The estates department has provided you with the following work description and has asked you to develop a deterministic schedule. So draw a clear network diagram using precedence diagram method, clearly highlighting early, late start times and slack of each activity, and also highlight the critical path. So here we can see the reason why it is called a deterministic schedule is that all the subcontractors have provided you with a deterministic time frame. So subcontractor has given you a 12 weeks period, and superstructure has given you an 18 weeks period. Now we could use this to first of all plot our network diagram or a logic diagram. So this is an identifier. Usually the software also makes use of an identifier. So here we can see the first activity is activity 10, which has got no predecessor relationship. So 10 will be the first activity, and then this is activity, the superstructure has got a predecessor, which is activity 10, and there's a finish to start relationship. So the next activity is 20, which has got a finish to start relationship with activity 10. The activity 30 superstructure has got finish to start relation with activity 20. So again, it's a very linear sort of a uh, relation. The activity 40 has got uh, finish to start relation with, so sorry, it should have been 30 here, 40, again a finish to start relation, and then the activity 50 has got a start to start relation with a lag. So for activity 40 afterwards, we have not got a finish to start, but it's a start to start with a lag of 40, and this is activity 50, right? So just looking at this relationship, we would plot the network diagram. So here is a much clear perspective of a network diagram. So here you can see the first activity. In particular, you would need to see that interior has got a start to start relation with exterior. So if we look at interior, has got a start to start relation with superstructures. So right, so here superstructure, and then we are not bringing this arrow from the end, rather it's coming from the start, which means that this is happening concurrently. We do not have to wait for the superstructure to finish before we start works on interior. When the work on superstructure starts, all we have to do is give a time lag of 6 weeks, and then we can begin work on the interior. Likewise, if you look at the services, it is indicated that services has a start to start relation with a lag of 10 with activity 50, which is interior. So again, you can see the relation here is start to start with a lag of 10. And also services has another relation with activity 30, which is superstructure, and this is a finish to start relation. So just looking at this relation, we draw the network diagram. The key reason for the network diagram is that it tells us the logic of how this project will be executed, which activity is following which activity, and what sort of a relation exists between different activities. Is it a finish to start relation, or is it a start to start relation with some lag to it? So that is the first job. So for those of you who missed the first lecture, and that is what we did discuss. That first thing is to draw a logic of how different activities will be undertaken. Once you have done that, the next thing is for you to do a forward pass, which helps you calculate the early start and the early finish times. So we, while manually scheduling, assume the project starts at day 0, and the duration is given in the box here. So we add this to give us the early finish of this activity, and this early finish becomes the early finish, early start of the subsequent activity, and then we add the duration to give us this. The only thing that we have to remember while doing a forward pass is that when we come across a merge activity, so for instance, this is called a merge activity cleanup, because it is merging 3 different predecessor activity, which includes exteriors, which include interiors, and which include services. And the question is, which duration shall we use? So if we approach it from this direction, it will be 40. If we take it from this direction, it will be 44, and if we take it from the bottom, it will be 48. So we remember that while doing a forward pass, if we come across a merge activity, uh, in doing a forward pass, if you come across a merge activity, you have to always choose the largest of the value. The reason is that, for instance, if you have chosen a 40, for instance, that would defy the logic, because you will be starting cleanup without finishing the activities as was required. So in case of a forward pass, we choose the largest activity. And this is reversed when we do the backward pass. If we come across a merge activity, then we will be choosing the smallest of the values. Okay, so you could have a look at this example and see how these critical path method calculations are done. If you so desire, it's a very simple example. You can take it to a scheduling software of your choice, maybe Primavera or Microsoft Project or Synchro, whichever one you like, and maybe compare the manual solution with the software solution. Right, so that was the uh, example of deterministic scheduling. Now we move to probabilistic scheduling. So it's a bit of a rehash of the same problem which we were doing before. The estates department would like you to put together a probabilistic schedule for construction of an apartment building. Letters were sent out to each of the subcontractors requesting their expected completion time for each activity. So the general contractor believes that it will take 8 weeks to complete site preparation, give or take 2 weeks, and that the substructure can be finished in 12 weeks, give or take 3 weeks. So here you see the probabilistic time values are given. So if we read through this, the general contractor believes that it will take 8 weeks to complete site preparation, give or take 2 weeks, right? So if you look at the site preparation, the subcontractor is telling us essentially it is going to take 8 weeks to complete, but give or take 2 weeks, which would mean that the optimistic time to deliver this activity is 6 weeks, and the pessimistic time would be 10. So give or take 2 from the most realistic time of 8. And the substructure can be finished in 12 weeks, give or take 3 weeks. So the substructure uh, subcontractor is telling us is most likely uh, going to take 12, but give or take 3 would mean that it would be the optimistic time would be 9 weeks and the pessimistic would be 15. The steel subcontractor would like to finish erecting the superstructure in only 15 weeks, but thinks it will take probably 18. However, any mechanical problems will lead to a serious delay of the superstructure due to concurrent project using other resources and could result in the activity taking as many as 33 weeks, right? So here we can guess that from this description, the most likely or optimistic time is 15, but thinks it will probably take 18. The most likely is 18, and the any problems with the mechanical problems would lead it to be completed in 33 weeks. And likewise, we can continue this concerned the general contractor who said that any problem with the superstructure could carry over to them, causing the exterior to take as many as 18 weeks. He said if everything goes as planned, the exterior will be complete in 6 weeks, which is also the earliest it could be done. So exterior subcontractor is telling us basically his optimistic time and mostly realistic time is 6, but the worst case scenario could be 18 based on the problems with the mechanical works. And then the interior contractor said there is a chance the interior could be completed in 5 weeks if they do not pick up any more jobs. However, he said he expects to be finished in 14 weeks and definitely within 23 weeks. So optimistic will be 5, most likely will be 14, and the pessimistic time will be 23. So basically, we will be looking at this, and then we will be using some knowledge of probability to work out the expected activity duration and the standard deviation. So the formula to compute the expected activity duration based on the probabilistic times which have been provided is A, which is the most likely time, plus 4 times the most, sorry, A is the optimistic duration, plus 4 times the most likely duration, plus the pessimistic duration divided by 6. So that would give us the expected activity duration based on the probabilistic methods. And we can compute the standard deviation, which will give us an idea about the risk factors involved. And so just to repeat, In a PERT method, for each task, the expected time is calculated uh, using the formula, which is optimistic time plus 4 times the most likely, and plus and the pessimistic time divided by 6. And from this point, the process for establishing the net is identical to critical path method. So the rest of the process is the same. So rather than using the deterministic time frames as we were assuming before, here now we will be using these values to do our CPM calculations. In addition to estimated time, the variances of each task is calculated to measure the uncertainty of the event using this formula. Okay, so now the problems that we see in the construction projects is that, in particular, statistical analysis is often not well understood by managers, especially the concepts of standard deviations and confidence limits, and as a result, uh, you will see very limited application of PERT methods applied in construction projects, and many software tools support PERT analysis, and often CPM PERT analysis is used interchangeably. So here you can see the beta curve, where this is the optimal time, this is the pessimistic time, and this is the most probable time, and based on this, using this formula, which is optimistic time plus 4 times the probable time plus the pessimistic time divided by 6, we calculate the expected activity time, which is then used to do the remaining CPM calculations. So we have covered this. Now we will talk a little bit about different concepts about schedule compression or project acceleration. So can you reflect on what could be the possible reasons that could prompt you to uh, try to squeeze your schedule, to compress it, or maybe accelerate your project? So there could be a number of situations, right? So things may have uh, so late materials availability, or some, for instance, you have met unexpected conditions which you have not foreseen, which is very probable in the construction projects. It could be adverse weather conditions. It could be sometimes the changes in the client requirements, which could cause a delay. So there could be a number of different factors. So here some suggestions are, maybe you had made some mistake in the initial schedule. It's maybe a low productivity you have encountered. There could be problems in the resources, or your initial schedule was not realistic. It was too optimistic, and once you jump on site, you think that things are taking much longer than what they were originally planned, or the project demand earlier than expected. It could be sometimes fast market changes. So, for instance, if it's a retail project, the retailers want to be ready for a Christmas season, and they are pushing you to deliver the work quickly. And it could be this, or the project has slipped considerably, making up for the lost time recovery schedule, or you want to avoid the contractual late penalties and liquidated damages which result from project delays, or contractor's normal finish date does not meet the contract finish date. So this may mean that you have to uh, explore opportunities for compression or acceleration, or contractors want to move to another job. They think there will be more potential profitability by delivering work earlier, so they may decide to maybe do double shift work on this job so that they could release their crews and move on to the other job. Or sometimes there are political pressures. um, yes, the public relationing could be one issue, or you have borrowed heavily from the banks, from the investors at a very high interest rate, and you want to do the job quickly so that you could, for instance, if it's a building, you could operationalize the building and generate some cash flow and reduce the interest payment. So there could be a number of different reasons. So very often we have this misconception that if we have planned our project, that's it. It is not the case. The plan document is just a live document which has to be reviewed on a very regular basis to ensure. So there could be a number of different situations which would prompt us to explore opportunities for compression or acceleration. So here is one of such problems which are discussed in this problem. So this problem talks about a dam construction project. So the table below gives activities involved in the first phase of the construction of an earth dam. The duration, the predecessors, and the budgeted cost of the activities are listed. The project had a physical constraint. Because of a low flow, the river must be diverted in the January of the next year, right? So definitely we have been alerted that this activity has to take place in maybe January of the next year. So let's assume it's 2021. So the question here is, first of all, tell us, if that is the case, when shall we start the work on this project? Choose an appropriate date, week, and month number for the project start, neglecting the holidays. Now, this is a very simple uh, problem. So all we have to do is firstly draw a network diagram and then have a look at so if we see the first activity is establish the site, the second activity is drive the diversion tunnel, and you can see the predecessor relation. So this activity B, drives the diversion tunnel, depends on completing establishing the site. So good. And then the third activity, concrete diversion tunnel, which is activity C, depends on completion of activity B. Then activity D, which is drive diversion tunnel west, only depends on completion of activity A. And then activity E depends on activity D. Activity F depends on activity A. Activity G depends on activity F, and the last activity is H. So that's this gives us the basically the logical sequence. Now, once we have done that, we could do either a very detailed forward or backward pass calculations, or we could do a very simple calculation. So we know the duration is given here. So this is 6. Activity D has a duration of 6. Activity E has a duration of 8. Activity B has a duration of 12. C has a duration of 14. H is a milestone activity with 0 duration. F has a duration of 3, and H has a duration of sorry, F has a duration of 3, and G has a duration of 6. Right. So we calculate the overall duration of different paths. So the first path going through the top is ADEH, ADEH, and we have a total, so 8 add 12, which gives us a duration of 20. The middle path ABCH has a duration of 12, add 6, add 14, so that would be 32. And the path at the bottom has a duration of AFGH, which is 6, add 6, 12, add 3, 15. So of these three, the longest path is the path in the middle, which is basically over critical path as well. So it is basically telling us that this project is going to take 32 weeks to complete. So they have asked us, when shall we start the work on our project? So we know, well, if you want to deliver the project in you have to, so if you draw a timeline somewhere here, we know one of the milestone is January, and let's assume this is January 2020 and this is January 2021, and we know that this project is going to take 32 weeks to complete, which is our critical path, and we know in total there are 52 weeks in a year, right? So we have to work from here and go back 32 weeks, and basically this will give us that we should commence work on this project on the week 20 of this year. So the week 20 could be somewhere lying around end of April or 1st of May. So let's make a suggestion that the work should start in the first week of May, which would allow us to do. So this is just simple back of the envelope calculations to help us compute the total project duration and give the time. Okay, so that is fine. But the other question here was assume that the project starts on the date chosen. So let's assume we suggested that the project should start in May 2020 and it has started in May 2020. However, what happened was that the contractor encounters unexpected ground conditions during construction. This increases the duration required to drive the diversion tunnel um, activity B and D by 25%, right? So unfortunately, what happened as we started work on this project, the duration of activity B jumped from 12 to by 25%. So it moved on from 12 to 15 weeks. And likewise, activity D went from 6 by 25%. So I guess 7.5 weeks. How can the contractor deal with this situation to achieve minimum increase in the contract cost and so they could deliver? Okay, so first of all, let's discuss activity D. Now, activity D lies on the non-critical path. The critical path here is ABCH. So I believe we could do calculate the slack, but the slack would be good enough to tolerate this increase. So we do not need to worry about so much about activity D. It's a non-critical activity. A delay of 25% could be accommodated through the slack. We could do a bit more detail forward pass and a backward pass to work out slack. However, the problem with activity B is that B was lying on a critical path, and a delay of activity B by 3 weeks mean that we are left with no other option but to somehow work how we could cover up from for that time from the subsequent activities, because otherwise this 3 weeks 25% increase in time duration will cause delay in start of activity C, which will mean that we will not be able to divert the river in the January, in the beginning of a January. Perhaps it would be a third week of January. So the only way for us to address this constraint is to work out with the contractor C and try to get C from 14 to down to 11 weeks. Now, how do they do it? That's something which has to be discussed with the subcontractor. So it may involve doubling the shifts or whatever, right? So we did discuss there will be a number of different situations which will prompt us to accelerate our project and do activities considerably. Now, when we do things in an accelerated manner, the term we often use is called crashing. So here you are given an example, the task A with the duration of 10 days and a cost of 3,200 pounds. So this is the normal time, and that's if you ask a subcontractor maybe how much time you would take, for instance, if it's maybe we are putting a new toilet in the house, and they will give you the normal time. So they will say, well, we will bring 2 workers and we will give you a normal time of 10 days, and the normal cost for the project will be 3,200. But if you are in too much of a rush, so you say, well, we can't accept the disturbance for 10 days. Cannot you do bring 4 workers, for instance, and get it done for us quickly? So in that case, the contractors will make, in this example, is making a suggestion that they could deliver the work only in 4 days. However, that would cost you 5,000 pounds rather than the normal cost of 3,200 pounds. So in this particular example, the crashing cost is computed as 300 pounds per day. So this is referred to as a crash time, which is 4 days, and the crash cost is 5,000 pounds, right? So normal logic suggests that it's good to work with the normal duration and the normal time, but there could be situations, as we discussed before, which may prompt us to explore the crash time and the crash costs. So, So the the yes, that's right. So the crash cost would be 300 per day, and total would be 1800. And this should be, yes. So I think on that basis, we can say that crash time would be uh, 4 days, and the crash cost uh, will be so. So the new cost to deliver the project in an accelerated manner will be this. Right. So in this particular example, the normal time to deliver this project will be 10, and we are delivering this project in a four days duration. So we will say that the crash time is 4 days, not 6 days. Right. So a few terminologies that we have to get ourselves acquainted with. Firstly, this is called the normal activity or normal time. So in this previous example, the normal time was 10 days, and then we have got this cost on the y-axis, which is referred to as a crash cost. So in the and this is the slope, and this time is referred to as a normal uh, sorry, this cost is referred to as a normal cost, and this cost will be referred to as a crash cost, and this time will be referred to as a normal time, and this time over here would be referred in a crash time. And this slope refers to as a crash cost per unit time. So the question here is, why do you think the crash costs are higher than the normal costs? So I think that's almost a rule that whenever you accelerate things, you have to be willing to pay a bit more for the cost. So yes, that could include premium rates. It could include more labor. It could include possibly labor working in overtime in the two shifts, um, things of those sort. So usually when we crash an activity, either we would need extra labor, or we would need some extra equipment, or material acquisition and delivery, earlier delivery charges, right? So whenever or there's an extra supervision of the work in progress, or extra administrative staff. So whenever we explore the acceleration, we have to be taken into account the extra costs that would come with it. Right. Uh, so how do we crash a CPM network? Basically, this tells you the heuristics. We will do an example which will make things a bit clear. So you select only the tasks within the critical path. These activities determine the end date of the project. So if you are given an opportunity to crash an activity, there is no point in crashing a non-critical activity because that is not going to reduce your overall project duration. So this is the first important aspect. It has to be an activity which is a critical activity. Within the tasks, to select the ones that result in time reduction at the least cost possible, that is the tasks that have the least cost per crashing day. So if you are given an option, for instance, you could crash activity A, and that is going to cost you 100K per week, and you can crash activity B, that is going to cost you 120K per week. According to the heuristics, you have to choose the least value, and you have to repeat, because your critical path will change. After, you will do the crushing on a day by day basis, and after each you would recompute the critical path. But if you are given an option, you will go for an activity with the least crashing cost per day. There are three factors constraint the network crashing. So crashing capacity, existing of buffers in the parallel tasks, and the parallel critical path. We will go through a few examples. So here is this network shown. Activity B and H can be reduced by 2 weeks. Which one shall be reduced? So here we are talking about a situation where you have been given an option by the subcontractors B and the subcontractor H, that they could potentially reduce their work by 2 weeks. So my question is, which option would you take? The option to reduce activity B from the existing 4 to get it delivered in a 2 weeks period, or would you prefer reducing H, which is currently 6, and delivering it in a 4 weeks period, right? So you're managing this project and you are given an option to reduce the duration, and the options are either activity B or H. And let's assume a situation that you are very keen to get this project delivered not in 22 weeks period but in a 20 weeks period. So you are keen to get this project done and dusted 2 weeks ahead of schedule. So the question is, which option would you go for? Option B or option H? Good. So it would be option H. So you can see firstly that uh, what is the critical path running through our project, and based on this you will identify. So if I could get my, sorry, highlighter working. So here you can see the slack is shown here, and this is the slack of all activities with zero slack. So the path of all the activities with zero slack, which is running through here. So this is the critical path which is running through the project. So if you crash a non-critical activity which is not lying on the critical path, it's not going to bring any benefits. Your project duration will still stay at 22 weeks. So it is important that when you crash, it has to be an activity lying on the critical path. Crashing a non-critical activity could incur extra cost for your project without bringing any benefits in terms of time. So in terms of a crash analysis, some of the key steps which are involved is you start with creating a critical path, then you list number of days each task may be reduced by, then you list cost of reducing tasks by 1 day, uh, reduce the task along the critical path by with at least cost of the reduction, and then you will recreate the critical path. And this process will be done again and again, because basically after uh, each crash by 1 day, your critical path could potentially change. So that's why we do not do more than one day crashing in one step. Okay, so we will take this very simple example to go through what are the steps involved. So here we are given this project. Here the first activity is activity 1, and the normal time to deliver this activity is maybe 1 week, and the cost is £100,000, for instance. Right? You explore with the subcontractor that is it possible to crash this activity, and the subcontractor answer is no, this activity cannot be crashed. It could be, for instance, pouring the concrete, and concrete needs some time to set in, so the contractor A has outrightly refused. They cannot offer any crash, so activity A is out of question. This is an activity which cannot be crashed. Do you speak to contractor B, and they are saying that the time to deliver their activity is 3 weeks. Normal cost is 150,000, but they are saying that they have the potential to reduce it by 2 weeks, and this is a crash cost per week, by the way, and you will have to pay an extra 100,000 for. So basically, one option on the plate is either you deliver it at a cost of 150 in a 3 weeks duration, or uh, you could use both of these crash times and you could get it delivered in a 1 week, but you will have to pay a cost of 150 plus 200 for crashing so that will be 350,000 pounds. Okay. For activity C, the option was you could crash it by 1 week and that would incur. So one option is to deliver it in 4 weeks period at a cost of 200. If you decide to use this crash, so the new possibility will be to deliver it in 3 weeks at a cost of 250, unlike 200. Activity D, the normal time is 3 weeks for a 200. The crash cost is 60,000. So you can potentially deliver this activity in 2 weeks at a cost of 260 in total, right? So this crash time and the crash cost per week is given. Right, so let's do this optimization of a schedule and see how. So here the network diagram is shown, showing the logical sequence of the work. Now, mind you, here an X is written, which is a reminder because we have been told that this activity cannot be crashed. So we have put an X that is not crashable. So can you tell me what is the normal time to deliver this project? So we can see there are two paths running in this project. The path at the bottom, if we look at this path at the bottom, has a duration of uh, so thank you for prompting 12. So ACEF, we have got two paths here. ACEF has a duration of 8, F is 311, and A is 12, so 12 weeks. And if you look at the path at the top, which is ABDF, and it has a duration of 10. So we know that the longest path is the critical path. So ACEF is the critical path, and this is also it tells us the critical path tells us the total overall duration of our project. So the overall duration of this project is 12 weeks. Now, the next question is, what is the total direct cost to deliver this project, right? So we have been given the total normal cost in this column, and we have to compute the total cost. So can anyone give a go and compute what is the total cost? So sometimes students make an error that while calculating the cost, they only calculate the cost of activities lying on the critical path, which is not correct because you have to deliver non-critical activities as well. So the total direct cost to deliver this project is 1000K. Right. So now we will try optimization. So we will try to see if we could deliver this project in 11 weeks rather than doing it in 12 weeks. So we would like to explore what are the options. So just a reminder, we put 1x here because A is an activity which cannot be crashed. It's out of question. So that's why we have put an X here. So we can see from the top part that there are three critical activities here C, E, and F. And if we want to deliver our projects in 11 weeks, the only way possible is that we target one of these three activities. So let's see how much will it cost us if we decide to crash C. So if I decide to crash C, it is going to cost me 50K. If I decide to crash E, it will cost me 70K. And if I decide to crash F, it will cost me 90K. So which one you reckon shall we choose? So on this basis, we have decided to crash activity C. And mind you, C could only be crashed by 1 week, which we have decided to do. So what we would do is we will look at 4. And now in this new situation, we are delivering this in 3 weeks. Okay. And we have to remember that we have to pay an extra 50 grand for this, and this is the cost, and I'm going to put an X with it because C could be crashed by only 1 week, which we have already done. Rest of the table is going to be copied. It is from the top. So the only minor change is that activity C time has been reduced from 4 to 3, and X indicates that this activity cannot be any further crashed. So the cost that we have to pay is that we can deliver this project in 11 weeks, but it is going to cost us not 1000K, but in this new situation, because of crashing activity C, the new cost will be 1050K. Right. So we want to continue with our optimization, and we want to see, can we deliver this project in 10 weeks rather than 11 weeks? Again, we have to calculate where is the critical path, right? So if we look at the top, ABDF in this new setup has a duration of 10. And if you look at the part at the bottom, ACEF has a duration of 11, which indicates that the bottom path again remains to be the critical path. The top path is not critical still. So in the bottom path, A and C are already been crashed. So the only options on the plate are you crash E or F. So which one would you suggest we go for? So, um, so we have seen, if we have got these two options, E is going to cost us 70 and F is going to cost us 90. So we will use the heuristics, always choose the cheapest of the two. So we will not choose F, rather we will choose E. So activities change in this step will be activity E, and it will be at a cost of 70K extra to the project. As a result, the project cost will go up by 70K, and the new cost to deliver this project in 10 weeks period is 1120. Now, the other question is, shall I write uh, X with E? I should not, because it could be crashed by 2 weeks, and we have just used one, so it still has got a potential to be crashed once more. So that's why, while writing 3 here, I'm not going to put an X, because I can still crash it once more. 3 and other information remains the same. Right, so we continue our exploration, and the next target is to get this project delivered in 9 weeks rather than 10 weeks. So my next challenge is to get this project delivered in 9 weeks. Now I have to recompute the critical path, and if I check my critical path again, the path at the top has a duration of ABDF, has a duration of 10 weeks, and the path at the bottom, ACEF, a duration of 10, which basically means that both my paths have become critical, right? So my project previously had only one critical path. So here, for instance, this was the critical path, but now because of this crashing and squeezing, the entire project has become critical. Okay, so this is a natural reaction. Once you try to uh, compress your schedule, your project becomes more sensitive. So right, so someone suggested activity D should be crashed. It will not make any difference, because even if you crash D, the path at the bottom is a critical path, and your time will not go down from 10 to 9 weeks. So the only option that is left with you is that you either crash a combination of BE, because you have to target both the paths. Just targeting a single path is not going to make any difference. Or you crash DE, or you crash F on its own. So if we see, if we decide to crash BE, that is going to cost us 170. If we crash DE, it is going to cost us 130,000, and if we crash F on its own, it will cost us only 90. So The suggestion here is that if we crash f on its own, that is going to give us a better value. So we take a decision to crash f. So the cost for crashing f is 90, and it can be crashed only once. So in my next step, I will change the time of f from 3 to 2x, indicating that it cannot be crashed any further. The total cost of my project to deliver it in 9 weeks will go up. So 190 plus 90 to crash activity. So it will come to 1210, I reckon. Yeah, so 1210, and the activity which is crashed is f at a cost of 90,000. And what I will do is I will copy the rest of the table as it is. So 1x, so f will be 2x, and rest of the right. So at this stage, we will see if we could get this project delivered in 8 weeks period. So if we have to get it further squeezed, again, we have to see where is the critical path. If you look at the path at the bottom here, ACEF, it has a total duration of 9 weeks. If you look at the path at the top, ABDF, it has a duration of 9, which indicates that both paths are critical. So again, we have already crashed F, so the only option is either to crash BE or crash DE. So we did calculate it before. Crashing DE cost us 130 and crashing BE cost us 170. So DE is the cheaper option. So we decide to change DE at the cost 130. So adding 1210 plus 130 will give us 1340. So we rest of the table remains the same, and with D I will be putting 2, and with E I will be putting 2 as well, and with D and E again, they could only be crashed by once, which we have already done. So I have to put a cross here as well, indicating that this activity cannot be further crashed. Okay, so that's what we are getting ourselves into. So there are a few options on the table. We could deliver this project in 12 weeks period, costing our client 100,000, or we could deliver it in 11 weeks, costing the client 100,050, or 10 weeks, costing the client 1120, or 9 weeks, costing the client 1210, or 8 weeks, costing the client 1340. Now the question is, can we crash it and deliver it in 7 weeks period? Um, and we have to recalculate the critical path. So if we calculate the path at the bottom, ACEF, it has a duration of 8, and if we calculate the path at the top, ABDF, it has a duration of 8 as well, which means that both paths are critical. But the problem is that one of your critical paths, which is ACEF, has got all the X's, which means that this one of your critical path cannot be crashed anymore. So even if you crash activity B from 3 to 2, your project will still be delivered in 8 weeks. You cannot get it any further down. So you have reached a situation where your critical path cannot be crashed. So this is basically end of the road for us. We have reached a situation where the most important critical path cannot be crashed. So that's it. So we cannot deliver this in 7 weeks because it will still, the path at the bottom will still be there. So the project will take 8 weeks again. So this way we saw that we have worked out based on the direct costs, different options. Okay, so the prompt here is to reflect on what are the key risks involved with crashing projects. So we have to be conscious that first of all, it reduces the flexibility, so you have a float, and it increases in the criticality of all the activities. Basically, your project becomes much more risky. So it's a fine balance between time and risk that a project manager has to consider. So based on the previous example, we have calculated that there are few options on the plate. Either we could deliver it in 12 weeks and it will cost us 1,000 pounds, 1,000 K, or the other option is to deliver it in 8 weeks and it will cost us 1,340. Um, okay, so but mind you, these were just the consideration of the direct costs. So these are the costs which are associated directly with the tasks or the work packages associated. But very often it is important to consider the indirect costs, which would include things like site charges, keeping your site offices mobilized, and the indirect cost decreases uh, uh, prelim costs and things of those sort, right? So the indirect cost decreases because you have to keep your site mobilized for a slightly lesser period. So if you deliver this project in 8 weeks, your indirect cost in this example is 700K. However, if you deliver it in 12 weeks, you have to your indirect cost will be much higher. So it is important to take into account not only the direct cost but also the indirect cost. So if we look into this and try to work out what is the maximum value, keeping in perspective both the direct and the indirect cost. So if we deliver this project in 12 weeks, the client has to incur 2,000K. If we deliver it in 11 weeks, it is 1975. So 1970. So from this, it appears that if we decide to deliver this project in 10 weeks, that is going to give us an optimal cost. So we can put this offer. So this sort of graphs are often plotted and is also called cost time trade-off graphs. So this is just an example of the normal cost. So here you can see the normal cost um, in a 20 days duration is lesser, but if you crash it, your project total cost goes up. So a few things that we have to keep in perspective: crashing cost increase as the project duration decrease. So the direct costs and the crash cost is always higher. So as you move uh, on the left of your time zone, your crashing costs have this sort of a profile, whereas the indirect cost increases as the project duration increases. So, and the indirect costs have this sort of a shape. So the longer you are on the site, the more indirect cost that you would incur. So we usually take into account both combination of the direct and the indirect cost to make a decision. So here, for instance, if this is the curve, possibly this is providing us with the best time cost trade-off. So reduce project length as long as crashing costs are less than the indirect costs. So here you can plot a summation of both of these, and based on this, you can see that this zone is providing you with the total best project cost, which is the minimum total cost and optimal project time. Okay, in this particular example, this graph is indicating a rising indirect cost as your project duration increases. This is indicating the and the direct cost curve, and this is the total cost time curve, and this point, which is 10 weeks, is providing you with an optimum cost time point. Right. So within this coursework assessment, there are certain problems which we are encouraging students to do to get some confidence in problem solving. Now, many of you are experienced project managers, but again, this may serve as uh, a refresher. So here today we are going to discuss second problem set, which is focusing on critical path method analysis and dealing with change. And we will also talk about use of computers in this problem. So the learning outcome and a bit of a description. So in this case study, you will gain confidence in building and managing a project. Now work on this project uh, commenced on 1st of March 2019. So the schedule has to be done based on this duration. And you have to identify the early start, early finish, late start, late finish, and float for each activity, and clearly mark the critical path. So this is the network diagram. So we have done some previous work. So basically we have had some debriefing from our subcontractors. Based on this, we have worked out the logic. So you could print out this sheet and use it to compute the critical path calculations. And based on this, you can work out what is the float of each of the activity, right? So for those of you who are not here, we always assume project starts and day 0. So you will have 3 here, and then this 3 would move here, uh, and then 3 add 6 is 9, 3 add 1 is 4. Now this is case of a merge activity where we could either use 4 or we could use 9 approaching from here, and as it's a merge in the forward pass, we will be choosing the largest of the two value, because if we use 4, then we are defying the logic, because logic is suggesting that framing exterior wall could only begin when forming and pouring of slab is complete, and if we begin at week 4, we are basically beginning it before that. So that's not so. We always choose the largest of the two, and then we would do. So you can print it out and you can give it a go, and then you can compare your results with this. So here is a forward pass calculation. So for instance, if we take this example of a merge activity, we could have chosen either 18 approaching from this direction or 23 approaching from here, and we would choose 23, which is the largest. Likewise, finishing the electrical is a merge activity where we could have chosen either 32 approaching from this direction or 22 from this angle, because there is a connection here, and 24 from here, and we will be choosing the largest of the value, which is 32. Okay, so it's pretty simple. We will do the forward pass, and once you have done the forward pass, then the early finish of the last activity becomes the late finish of the last activity. So this basically 35 is the overall duration of your project, and then we do the reverse. So 35 take away 1 would give you a 34, then this 34 will be carried here, and 34 take away 2, 32, and this 32 will be carried to all the previous connections, and then 32 take away 5 would give you an answer of 27, which is clearly telling you this is not a critical activity, this is a non-critical activity. Whereas this 35 take away 35 0 float, it's a critical activity. So you will work out based on this, right? So suggestion is that you print out the previous sheet and do some manual calculations, and then compare your answer with the one which is given here, and just to make sure that you have uh, got a good understanding how to manually schedule a project. And once you have done that, then you have to subtract the box at the top from the box at the bottom to work out the float. So here, for instance, 20 take away 17 is 3, or 17 take away 14 is 3, so that's indicating a float of 3. Here 9 take away 4 indicates a float of 5 here, whereas 9 take away 9 is a 0. So this appears that all of the activities lying on this path are critical activities, so all of them have a 0 float. Okay, so here in this example, you can see the float which has been calculated. Um, Okay, so it will be provide some useful practice. You can print out this sheet and have a comparison. Also, I will be providing a Microsoft project generated solution to this problem, so you can have an idea about how you would be able to do the same problem using Microsoft Project or another software of your choice. So here we can adjust the layout. So this is a network diagram which is presented in Microsoft Project. Within a Microsoft project, you can enter the tasks directly from a network diagram view or a Gantt chart view, and you can adjust the layout, you can move it around to get a good understanding. So the reason for producing a network diagram is basically to tell us the logical sequence of how this project will be completed. So to have a big picture or bird's eye view of the project. This is some other example of the outputs produced by students when they do. So it is not expected of you to do. Uh, all that is required is if you could do some manual calculations and provide an evidence as part of a problem set that you know how to do the CPM calculation. So right. So once we have done that, we will um, discuss a few scenarios. So these scenarios begin with assuming the work commences on 1st of March 2019. You have to convert the work days to calendar days. Work does not take place over weekend or public holidays. So this is given as the project start date. So if you could convert this into a bar chart using 1st of March 2019 as the start date. Now, mind you, early start or early finish dates are of little to subcontractors responsible for completing the work, right? So you cannot tell, for instance, the roofing subcontractor that please turn up on the seventh day of my project. It would mean nothing to them. You have to give them a calendar date. So you have to tell them that, well, turn up on 1st of April, and you must be out of my site by maybe 5th of April. So you have got 4 days. So they understand they need to know the calendar dates when they need to report for this work. So in this, your assumption is work is starting on 1st of March 2019, and we use 5 days work week. So standard shift 9 to 5. Convert the work days to calendar days. Note that work does not take place over Sunday or public holiday. Okay, so you can use a sheet like this to convert work days into calendar days. So here on the top layer you can see are the work days of your project which are running concurrently 1 2 3 4 5 6 7 8 9 10 basically. And this is the calendar days. So 1st of March is a Friday, and then second third no work is taking place. So basically the second day of your project is the 4th of March. And likewise, if you take this example, the 14th day of your project is 20th of April, and the 22nd day of your project is 1st of April. So basically convert the work days of your project onto calendar days. Okay, so so if we take an example, so the first activity here is excavation. Okay, excavation is a activity which is taking place from 0 to 3. So work is taking place from 0 to 3. If I'm scheduling it based on the early start time, so and I've got no float here, and so basically it means in calendar days it's taking place from 1st of March to 5th of March. And then the second activity is form and pour the slab, right? And the slab is taking place for 6 days from 3 to 9. So, and the third activity is temporary power, which is taking place from which can take place from 3 to 9, but it has actually a duration of only 1. So it the let's if we are scheduling it on, right, so it has got a float of 5 days, and the work is taking place on the first, right? So likewise, you would plot a bar chart in basically converting the work days into calendar days, right? So as I said before, the work days maybe of not such a great deal of interest to the subcontractors because they would have to schedule their work based on the calendar days. So this way you would convert that. Okay, so this is an example of how your bar chart should look like if you have done it properly. So you can see the workdays are indicated by the orange color here, and the float is indicated by the yellow. So if we take, for instance, any at random, for instance, framing the exterior wall, right? So this is has an activity which is a zero float, and you can see here there is no yellow bars here, and this is a 5 days activity which is taking place strictly in this time. Whereas if we pick on an activity which is windows and doors, so windows and doors have a slack of 3, which is reflected by these 3 yellow lines here and the orange boxes, right? So it may be worth giving it a go. This is an output produced by one of the students. Okay, so and they have done a similar thing. All right, so we will discuss a few things. Firstly, discuss how you will communicate project schedule information with the project managers, with your owners, and the subcontractors, right? So when it comes to information sharing, we cannot share all the information with all the stakeholders, so we have to be sensible in this. So for instance, if it is for the project management team, so this is a software output produced by Microsoft project of the same project which we were discussing. So the work has started and it has got all the information about the float. So you can see shingle roof, for instance, has got a very healthy float built. And now these activities on the top, the exterior phase, these are referred to as a summary activity, as it shows the high level of the work breakdown structure, and then so the work is split into exterior phase and interior phase. So uh, uh, I will be making a copy of this schedule done on Microsoft project available, so you can use it for comparison purpose. Right. So the problem is that if you share all this information, it's possible that your subcontractors may not turn up on time, and they could possibly feel the liberty to use and eat up all the float without your permission. So the float is sort of a leverage which the main management team has to keep to its heart. So you will not like to share this information with all the stakeholders in a classical situation. So this is an example. The one which we saw is a project manager's bar chart, which is clearly indicating all the information, all the float. Now this could be produced maybe in a tabular format. So if you're using a software, you can take a output in form of a tabular format if you prefer that more clearly. So this is indicating the duration, the total float, the early start, early finish, late start, and late finish time. So this is telling you what is the maximum delay we could have on this activity if we decide to work, right? Right. Now, when we communicate with owners, the tendency is that we usually do not share the information based on the early start and the early finish times, because for instance, if we fail to begin the work in the early start time, despite uh, the fact that we still have got the float, it will generate an unnecessary stress. The owners may think the work is being delayed, whereas it is not. So very often we communicate with the owners based on the late start and the late finish timing. So rather than sharing all this information, we will only be sharing this table, which is going to tell them that what is the latest possible time by which the work should be finished. So if it is done early, that is to an advantage, but it will not. So here in this example, we see that when we are communicating information with owners, we are communicating based on the late start timing. So all the float is being used upfront, which is indicated here. And this is the non-critical activity, and the critical one shown in the red. So we are just communicating information based on the late start and the late finish time. Right. So when we communicate information with the subcontractors, we don't want to give them the late timings, because then they could. So we will be sharing the early start timings, but we would exclude the information of the float. We do not want the subcontractors to have this liberty to use the float on their own. This is something which management team will be keeping. So all the dates are early start and early finish, and float information has been removed when we are communicating information with our subbies. So we will talk about a few problems in this scenario. So the description is: the work commenced on above project according to the schedule. Things were going according to the plan. John was a carpenter involved in framing of exterior walls. He started work on schedule. However, 2 days after commencement, he gives you a ring informing that because of the weather-related factors, framing the exterior wall will take 7 days to complete rather than 5 as originally scheduled. Is this a problem? Is there a need to inform the project client at this stage? Right? So you are running into a situation where one of the subcontractors was working on this task, framing of exterior wall, is telling you that well, the initial plan was to deliver it in 5, but now it is going up by 2 days, and they will be the new time is 7 days. So is it a cause of a concern or not? So we have to go back to our bar chart to see where we stand with this. So this is the particular activity, framing of exterior walls. Will you be concerned if this activity gets delayed by 2 weeks, 2 days, sorry? Yes, so this is obviously a critical activity with no float available. Okay, so it is very important if you have an agreement with the owners to get the project delivered by 18th of April or within 35 days. This is not going to take place by 18th of April, and your project is getting delayed, and a good proactive project manager must keep everyone informed. So in this spirit, you will have to inform this delay to the client that the project will no longer be able to be delivered in by 18th of April, which I presume is the agreed on date. So we continue with the scenario. So you call in the project client, informing her that the project will be delayed by 2 days as a result of the previous delay. She does not like the sound of this and asks you to ensure that the project is delivered as per the contractually bound agreed upon schedule, or contractor is liable for liquidated damage due to the delay. So here we are dealing with a client who is adamant that the deadline is a deadline, and that has been agreed. She is not flexible on that. Now, to deal with the situation, you speak to different subcontractors. Now, contractors working on windows and doors and painting the exterior activity are offering you an opportunity to accelerate their delivery by 2 days for an extra cost. Will you take this offer? Okay, so let's go to our bar chart again: windows and doors and painting and exterior. So windows and doors and painting the exterior, both of them have offered an acceleration by 2 days, right? So basically, this guy is telling you I can deliver the work not in 3 but in 1 day, and this guy is telling you I can deliver the work not in 3 by 1 day, but none of these activities are critical, and even if you crash them, you would possibly incur extra cost without incurring any benefit. Your delay would stay the same, right? So I think uh, that's a good answer. This offer can be declined. We do not stand to gain anything. So question is, which activities you can consider for acceleration to get back on schedule? What will be your key decision-making criteria while selecting activities to accelerate? So if you are offered with a choice to accelerate, which are the activities that must be targeted for acceleration? So good. The answer is critical. So there is no point in accelerating non-critical activities. So you can look at which are my critical activities. So you can highlight and maybe speak to those subcontractors which are following the delayed activity, and see if any of these, because the only way for you to get back on track to recover the 2 days lost is to attack a critical activity. Crashing a non-critical activity will not bring any advantage. And what practical strategies can be deployed to accelerate project activities? So usually we deploy extra labor or bring in extra equipment. So we discussed previously some of the strategies that could be used. Now, project client just called you and he wants to explore if you can pour a 12 inches thick slab instead of a 6 inches as was originally planned. At the same time, she wants project delivered on time and is not granting any extension of the contract time. So as a favor, she is asking you, can you do pour a slightly thicker slab? And she is not flexible with the timeline. So as a courtesy, you check it with the relevant subcontractor who tells you the time to form and pour a 12 inches slab will be an 8 days job. So will you still entertain client's request as a good gesture? Client is not willing to give you extra time allowance or cost, and what other choices are available to you? So if we check our bar chart and have a look at forming and pouring of a slab, so this is a software output. So um, so we are in a situation where client is not granting us any extension and they're still wanting us to do forming and pouring of slabs, which is this activity. And the contractor is telling us that they could do it, but it will be, I think previously it will take them 3 extra days. Okay, so what answer shall we give to the client in this situation? An answer of yes or a no, or any thoughts you have? So I think one thing which you can clearly see that this is a critical activity, and she is suggesting to cause a delay to a critical activity. So any delay on a critical activity means that you will not be able to deliver this project on the stipulated deadline. Addition of 3 days will trickle down to the project deadline. So at some time, very important to learn to say no as well. So I think, and the logical answer would be to, given the constraint that she is not granting any extension of the contract time, and she is asking you to delay a critical activity because of a change in specifications, the answer would be no. So suggestion will be you're importing unnecessary risk into the project. Yes. So moving on, the contractor working on installing adding activity started on time, but because of delayed delivery, ended up taking 7 days to complete rather than 4, which were originally planned. Will this delay? So install sliding activity has got 3 days time overrun. Yeah, siding. Okay. Uh, so what actions will you take after knowing that activity installed siding is now taking yes, it's a US based scenario. So if we look at install siding, you're right. So install siding has been delayed by 3 days. So will you be concerned with this? It is not a problem. You have got a lot of float, so you can easily accommodate it within. So this, you should not worry too much about this delay. Having said that, it is always important to check your network diagram. So let me go, and this is the install siding activity. And a delay of 3 days, even though it's a non-critical activity, will delay the subsequent activity, which is painting the exterior. So as soon as you know, you have to inform the painting the exterior guy that your job is not starting on the day 21 of my project or whatever it is on the calendar, but rather, so it is important that you do inform the subsequent subcontractors. Even though it's a non-critical activity, it is delaying start of others activities which depend on and this activity. Uh, we continue with this project owner just called you. She has decided to change roof shingles asphalt to tile, and you speak to the relevant contractor who informs you it will take 7 days to install rather than 5 as originally planned. Will that affect the project completion date, and what will be the course of action? So, shingle roof here again, you can see this is an activity which has got some float built into it. So again, I think you should not worry too much. However, you have to see the network diagram to see if it and the delays are having any impact on any other subsequent activities which follow, right? So task A. So this is a problem set where thought that students could provide some evidence that they have gone through it. So this is an optional activity which you don't need to do. But here the project client has asked you to send her a computer generated project network diagram, clearly highlighting activity duration and sequence of tasks. So using a software tool of your choice, which could include things like Microsoft Project, Master Project, Primavera, or Synchro, or I think there are a number of other tools. You could draw a network diagram, and final output could look similar to this. Again, an optional task, you can assign resources to the task. So you can assign different subcontractors responsible for different work packages. To assign resources, you will first need to define resources in the resource sheet view. Once resources are defined, then you can highlight the task. So in this particular problem, these are sources which are, and these are the subcontractors. This is the name of the subcontractor involved, and there are some notes which we want to leave for the subcontractors so that and they could see these notes. So we can upload this information, and this resource information within the software overview, so we can assign the resources. So there is a version of this file which is available. So it is always good to do one problem manually and then maybe compare your approach to the computer so that you could uh, uh, compute. So here is a desired Gantt chart view after assignment of resources, clearly indicating critical path and float for each activity. So here we have defined three subsequent activity. Okay, right. So you would have access to this is in the session 3 notes. I will just send a reminder email as well with a PDF file, so you could access a Microsoft project solution to this. So you can have a viewpoint. If you're not able to have enough time to develop it, you can just see uh, um, one working draft. Right. So in terms of some additional reading, and there is a link to this Microsoft project for construction schedulers, a useful document which delves deep, and there's a link to Microsoft project step by step. So there are two of these links which are available, which you could explore. Okay, so I think that's all that I wanted to cover today, and